In a previous, more general video, we discussed where conservation of energy is a concept that allows you to always track where energy goes. And in that particular video, we used a power plant as an example to track where energy goes, so it makes it all the way to, say, a light bulb in your room. In terms of physics, though, we have to be a little more specific about it and sort of hone it down to some more particulars that we'll deal with in this particular class. Now, in physics, we have two types of energy. We have kinetic energy and we have potential energy. These are types of energy just like the nuclear and the coal and the light bulb and so on that we can use to sort of track where the energy would go. Now, kinetic energy, of course, always has the singular definition of 1/2 mv squared. So if something's moving, it has kinetic energy. And now potential energies can take many different forms. We have mgh, which is gravitational potential energy. We have 1/2 k delta s squared, which is spring potential energy. And then we might even have potential energy due to a pendulum, 1 minus cosine theta, say, where theta is the angle that the pendulum has been pulled back to. So we have these potential energies going on, and what conservation of energy will mean for this particular setting, with these types of energies we have in a physics class, is then that we'll be tracking the flow of energy, say, between the kinetics and the potentials. So, for instance, a ball's speed could be transferred into its gravitational potential, which then might go back into a kinetic, which might go back into a pendulum, or might go back into a spring. There's all this interplay of energy going between kinetic and potential, and we can apply the concept of conservation of energy in tracking where that energy goes by being very careful in our understanding of a problem to see that how the energy might go from kinetic to potential and back again. As an example of that, let's consider a ball that's moving as a projectile. So here's the ground, and let's say the ball is going to be right here on the ground, and we're going to shoot it off in this direction with some velocity v, and it's going to go off with some angle theta. So what we can do then is let's see if we can track the energy of this ball as it flies through the air, much like we track the energy from the power plant to the light bulb the way we did in another video. So we know just sort of generally that the ball is going to do a trajectory that's going to look something like this. And well, what would you expect? Well, down here, since the ball is being launched but is straight all the way on the ground, the ball doesn't have any potential energy, but it has a lot of kinetic energy. So what we'll do then is we're going to represent our conservation of energy ideas here by drawing what are called these energy bar charts here. So we'll just do a bar chart like this. So just as the name implies, this is going to be a bar chart, or in this case, an energy bar chart. So what we'll do then on our bar chart is we'll have kinetic energy here, we'll have potential energy here, then we'll have total energy right here. Now, total energy is always the sum of the kinetic and whatever potentials might be in the problem. So down here where the ball is being launched, it has a tremendous amount of kinetic energy because it has all of this speed v that some launching mechanism has given it, but it's all the way on the ground, so it doesn't have any potential energy. Now, if I add the potential and the kinetic to get total, I'll get a bar here for my total energy, which is exactly going to be as high as that kinetic energy bar. So this height here should be the same. So that's what the bar situation would look like right there. Now what begins to happen then is as the ball starts to climb through its trajectory, again, we like to track its energy. When it gets up here, what we can conclude is because it's sort of gone up a bit now, is it's probably lost some of its velocity. It's not quite traveling as fast as it was right at launch. So the kinetic energy will be less. But we also notice here that it has some height above the ground now, some distance h above the ground, so it's gained some potential energy. So if we were going to draw the bar chart for this, illustrating conservation of energy again, same sort of setup here. We'll have kinetic energy, potential energy, and total energy right here. The way we'd have to draw it then is we draw a little bit less kinetic energy, something like this, and we'd have to draw some kinetic energy in there, but we have to be a bit careful because since energy is conserved in this system, it never gets lost. And so the total energy the system has from chart to chart will always be the same, the total energy. Just because it's risen up again a little bit against gravity in the idealized case here doesn't mean it lost any of its total energy. The energy is just getting redistributed, as we said, between kinetic and potential, the way we started out at the beginning of the video. So those have the same amount of total energy, and if I'm hypothesizing that at this point right here, this is how much kinetic energy the ball has, the rest of this bar, or about this much, must be in potential energy. So sort of draw it like that, noting again in particular that this small amount of potential energy is just enough to fill in this energy that was lost from kinetic because the ball is climbing against gravity, but the sum of this one and this one, the height of this one plus this one will equal a total energy like that. So that's what we mean by conservation of energy in physics, that we've just tracked where the energy has gone. So again, this bar chart has to do with this position, this bar chart has to do with this position right here. And we can sort of continue the process and keep doing that. Like in particular, if we reach the apex right here, at the very top, we could draw some another sort of energy bar chart for that, and we get kinetic, potential, in total again here. Now at the very top, the kinetic energy will be minimized here. That's where the ball has lost all of its vertical component of speed, but the horizontal still persists, as you'll find out in other lessons and things. But the total energy remains the same once again. The ball never loses any energy during its total flight. So agree that the kinetic is small, but the kinetic must have been lost and transferred all over to potential over here. And I'm not even drawing this the right height because it has to be the height has to match up with the total energy. So let's get that bar out of there. Take this bar out. Kind of messy there, but I think we still do it. So I meant to draw this as being the original part left over right there. There's the potential right there. So see, all across the board as the ball is made through three different trajectories over here, say A, B, and C, or 1, 2, and 3, all kinetic, distributed between kinetic and potential, and still distributed between kinetic and potential, but the distribution is always so that the total energy always remains the same. So there's your conservation of energy that we can write right off, and this will be the useful one for physics here, is that the total energy is always equal to the kinetic energy plus potential energy, and we can imagine then that the kinetic and the potential can slosh around exchanging energy like crazy, as they're even doing in this simple example right here. The kinetic here is given some to potential at the loss of a kinetic. As it moves over to this situation over here, the kinetic gives up even more for potential, and so on and so forth. And if we want to draw one last bar graph once again, like if we can draw this point right here, which is say the total symmetric point for this graph, we'd expect that this graph would pop up again, where you'd notice that some of this potential then would slosh back into kinetic as the ball speeds up as it falls again. So that's sort of the underlying principle between conservation of energy as it applies to physics problems, and the conservation part comes from that this term right here, the total energy part, is always going to be the same for these systems here. It's always going to be the same number. So that's not going to change, and that'll be a very powerful fact to use in terms of manipulating and solving problems algebraically using the principles of conservation of energy. So one more time, conservation of energy, we're just tracking where energy goes. In the case of these simple mechanical systems, it'll be the sloshing of energy between kinetic and different types of potential. And the very simple example we looked at was a ball being shot above the ground, where we saw the initial kinetic being distributed among kinetic and potential as the ball flew through the air, noting that the total energy always remained constant, which is the fact of conservation of energy, that the total energy is always the same number.